Hi, this recording will be the beginning of the 2.2 notes on density curves and normal distributions. Today's first lesson focus will be on density curves and empirical rule for normal distributions. You won't need a calculator for today, but you will in the next lesson. So by tomorrow, if you don't have a TI-84 on your computer, or if you don't have a TI-84 at home, or if you don't have an Inspire or some sort of calculator, you can download the app called Calculate 84. And that's free on your iPhone. It works just like a TI-84. So you'll see some of those steps tomorrow. But for today, again, you won't need one, but you may want to plan ahead and try to get one ready for tomorrow. So I'm going to go through the PowerPoint that goes along with the guided notes that are posted in Google Classroom. So you could pause this video anytime. I figure it's easier than doing a live lesson if I do a shortened version and record it. So here we go. And again, feel free to pause at any time. So you should see my screen here. So this is 2.2 density curves and normal distributions. Here's some learning targets. This PowerPoint is posted as well. So we're still talking about quantitative data. We probably won't go back to categorical data this semester until we review for the final exam. So we're focused here on quantitative data. And some things we've talked about in the past with this quantitative data is to, one, always plot your data, make some sort of graphical representation, and we typically then describe that pattern, describe what we see. So that's when we would talk about shape, center, and spread, and look for outliers. And then we also calculated numerical summaries to describe center and spread. So we calculated mean, we calculated median, standard deviation, and IQR. When there's some pattern, we can simplify it or make almost like a generalization based on it. And we do this with what's called a density curve. So let me show you what a density curve is. This is in your notes. Here's the definition. A density curve is a curve that is always on or above the horizontal axis and has an area of exactly 1 underneath it. And let me show you a picture here. So here's an example of a dot plot. So this is a graphical representation of some finite data. Looks like some kind of journey times in minutes, so how long to make some journey. If I want to fit a density curve to this, I can put a smooth curve or a continuous curve. This one's looks kind of uniform. If you look at the shape, I would describe it as uniform, almost the same height. So if I fit a density curve to this, it ends up looking like a rectangle. So because this is kind of uniform here, my density curve ends up being this flat line that fits the data. So let's kind of look at these two qualities. So it's on or above the x-axis. So here are my journey times on the x-axis. The whole distribution is above. The area is 1. So if you look at the height here, the height is 1/3. And if I look at how far it is from 2 to 5, well, that distance is 3. So the area of this big rectangle is 3 times 1/3, which is 1. So this meets the requirements of a density curve. This first semester, we won't really deal with density curves that look like this, maybe 1 or 2, but second semester, if you go on to AP, we'll see a lot of these. So we'll kind of say what I said. The overall pattern, this dot plot, of the amount of time it has to take Selena to get to the bookstore by train each day for the last 1,000 days can be described by a horizontal line. My density curve ends up being this horizontal line. Here's another picture of a density curve. So here's a histogram. This is the scores of all 947 7th grade students in Gary, Indiana on this skills test, this vocabulary test. So here's the histogram of those 947 7th graders. So if I want to fit a density curve, again, I kind of estimate the histogram here with the smooth curve over top. So my density curve is right here. Now the area, if you had calculus previously, you could find the area of this using integrals. We're going to call this a special curve in a little bit here called a normal curve, also known as a bell curve. Some other properties of density curves before we focus on the normal curve. The mean of density curves is the point at which the curve would be balanced. So picture it being either like a scale or like a seesaw. So the mean is going to be the point where the curve would be balanced on a seesaw, where it would lay flat. Whereas the median is the equal areas point, is the point that divides the area in half. So let's look at some pictures here. So here's a symmetric curve. So in a symmetric curve, if you picture like a seesaw, obviously the mean would be right here in the middle to balance this curve. It's the same on either side. So you have the same weight on the seesaw on either side. It would stay balanced. The median in this case splits this area directly in half. So again, because it's symmetric, the median cuts it right in half. We're equal area on the bottom, equal area on the top. Let's look at a skewed curve. So here's a curve that is skewed to the right. And if you notice, the mean now slides a little bit toward the skew. And we know that from chapter 1 that happens. But in terms of a balancing point, if I want to balance the weight of this curve, I need a little bit more to cover up for the skew. These skewed values are heavier. They're worth more than these values over here. So the mean kind of slides towards the skew. The median, again, equal areas is the median. If I were to calculate an integral in calculus, or if I were to calculate this area on either side of the median, I would find those areas are the same. So the median's kind of closer to the hump, and the mean gets pulled to the skew in general. So the mean and median are the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve is pulled away from the median in the direction of the long tail, or the direction of the skew. All right, some more properties here of density curves. A density curve is an idealized description of a distribution of data. So if I go back to that histogram of those ITBS scores, those vocab scores for 7th graders in Gary, Indiana, that smooth curve over the histogram is like generalizing for everybody. So yeah, I have these 900 some 7th graders, but that's what the histogram shows. I want to generalize for everyone so we can fit a smooth curve over that histogram. And it's an idealized or generalization of some bigger distribution of data. We distinguish between mean and standard deviation of the density curve and the mean and standard deviation computed from actual observations. We'll have some special symbols. We already know X bar is sample mean, and S is sample standard deviation. And I believe I mentioned in chapter 1, population means or density curve means we call the Greek letter mu, and standard deviation of a population, or for this, a density curve, a generalization. So based on some histogram sample, we generalize, we call that standard deviation sigma. All right, so the whole point of talking about these density curves right now is the world famous normal curve. So here's some pictures of some normal curves. They're very important. There's many things in the real world that end up, their data is relatively normal or approximately normal. Beautifully symmetric, right? Let's look at some of these properties. So the shape, all normal distributions are symmetric, single-peaked, and bell-shaped, regardless of their spread. Like notice, this is still, both of these curves at the bottom are symmetric, and they're single-peaked, and they're bell-shaped. It's just this one's a little more spread, so we expect the standard deviation here to be a little bit bigger. This one's a little narrower, standard deviation is just a little bit smaller. But in general, their shapes are always this symmetric, single-peaked, bell-shaped curve. Their center is always the middle. In the upcoming weeks here, you'll get sick of labeling this, but we'll always, always, always put the mean in the center. And the spread is always some standard deviation sigma. It'll change based on each normal curve. All right, so here's a formal definition that I think you can write in the guided notes. A normal distribution is described as a symmetric, single-peaked, bell-shaped density curve called a normal curve. Any normal distribution is completely specified by two numbers, its mean and standard deviation. So normal, and think about this, shape, center, spread. The word normal tells us the shape. It's symmetric, single-peaked, bell-shaped. The center will be the mean. So every normal distribution will have a distinguished mean. And my spread, my description of spread will be standard deviation, sigma. Here's some reasons why normal distributions are important in statistics. I'll just let you kind of read through these on your own. They are very, very common in real life. And we'll see it again. So we'll see it here looking at data, like in example 1 or in point 1. But reasons 2 and 3 will kind of be in the future. 2 will be when we talk about probabilities and chance outcomes, and 3 will be very much later on, really in AP, when we talk about inference methods based on normal distributions. The last thing we'll talk about today is something called the empirical rule. So what the empirical rule is, it's like a rule of thumb. It is not exact, so it is approximate. We're going to calculate these same proportions or these same percentages on Friday in the next lesson using a calculator that are more exact. But this is like you're walking down the street and someone asks you some things about a normal curve. Well, you can use this empirical rule right off the top of your head. You don't need a calculator. So what this empirical rule says, for any normal distribution with mean U and standard deviation sigma, approximately 68% of all observations fall within one standard deviation of the mean. So if I look at this picture here, my mean is 0, or if my mean is 0, in this case it is, within one standard deviation on either side, I have 68% of all values. And that should make sense. We expect in a symmetric distribution most people to be around the average. Next, approximately 95 of the observations are within 2 standard deviations of the mean. So here again, I start in the center, but I go out 2 standard deviations below, 2 standard deviations above. So between these 2 standard deviations are 95% of people. And then lastly, within 3 standard deviations, 99.7% of observations fall within 3 standard deviations. So almost everybody. You can relate this to test scores. Let's say SAT scores, they're known to be normally distributed. SAT every year will have some average. About 68% of kids will score within 1 standard deviation of that average. About 95 will score within 2 standard deviations of that average. And about 99.7 will score within 3 standard deviations of that average. So empirical rule, again, these aren't exact percentages. We'll find that tomorrow in the lesson, the second part of 2.2. But they are approximations. And last little thing here, they only apply to normal distributions. So you can't apply this to some distribution that's skewed or some distribution that's uniform. This applies to things that are normal. The homework is also posted in Classroom. I believe it's a worksheet just on empirical rule. So give it a shot and send me an email if you have any questions.